Okay, in this section we're going to consider some other side effects that accompany scaling MOSFETs. And a few of these are really parts of the reasons why constant E-field scaling might make more sense in devices rather than constant voltage. So let's remember that the E-field is really the physical quantity which relates to the properties of the material. So a voltage dropped over a certain distance gives you an E-field, and the fact that you take into account that physical size means that you're dealing with an intrinsic property of the material. So let's first look at oxide breakdown. And this one is relatively easy to explain. If you keep the gate voltage the same, but you shrink the oxide thickness, the E-field in the oxide is going to scale by that factor of K that you multiplied the thickness by. Two things can happen. The first is that the oxide has a certain dielectric strength, and that dielectric strength is a fixed quantity. The amount of current that you can flow through this oxide will be 0.0000000 until you exceed some threshold E-field, and then it'll go up to a large number. And this is the same thing, the same phenomena that you see when you scuff your feet on the rug and then touch a doorknob. The air has a certain dielectric breakdown strength, and so does an oxide layer. So literally lightning bolts start shooting through this dielectric, and you get parasitic conduction through the oxide, and you will tend to reduce your amount of charge control in the channel under the oxide, as well as inducing unwanted leakage currents. It can also result in physical damage to the oxide so that it doesn't work in the future. So physical permanent damage can be made to the device if too much gate voltage is applied over too thin an oxide. Now the second effect that can happen as the oxide gets thinner and thinner is quantum mechanical tunneling. So this quantum mechanical tunneling has no physical effects on the oxide. However, it'll make the leakage current go up in the device. And that means that the power draw of the chip overall, which remember consists of billions of these transistors, will be going up. Even in their off state, they'll be drawing power. That'll tend to heat up the device as well as requiring more power. So both of those effects are unwanted. Another effect that can happen, this time not in the oxide, but if we consider the depleted semiconductor to be a dielectric, we can also get the avalanche breakdown and carrier multiplication effect that we talked about in terms of the breakdown of normal p-n junctions. So remember that the MOSFET is really just two p-n junctions put together. So especially at these corners, the E-field will tend to build up. Remember that any object, the E-field around any object will be proportional to the radius of curvature locally. So a sharp point creates a very intense E-field and a multiplication factor on the average E-field. So the corners around the corners of the source and drain, and particularly the drain, are sources of low radius of curvature and thus E-field concentration. So even though the average E-field out here away from this corner might be below the threshold needed for avalanche breakdown in the semiconductor, at the corner that might happen. So the design of MOSFET dimensions and dopings has to take that into account. And we'll just remind ourselves that the avalanche breakdown threshold tends to be higher at higher doping. So the desire to make smaller channels with higher electric fields would call for higher doping in the bulk wafer. A somewhat related effect is the effect called snapback. So the phenomenology would look something like this. If we're looking at the source drain voltage and the current flowing through the drain, it starts out looking like a normal MOSFET, but then does a funny snapback effect. And this is because the MOSFET can actually be considered to have a parasitic bipolar junction transistor that runs in a path like this. So if we look at this path, it's NPN, which equals a bipolar transistor. And bipolar transistors are known to have this high current, low voltage state. So this is also related to the phenomenon called latch-up when you're looking at a CMOS structure having a P-body and N-body MOSFET next to each other in your logic circuit. Now the last mechanisms I want to talk about have to do with permanent modifications made to the MOSFET structure by either exterior radiation or, in a sense, by interior radiation, meaning hot electrons. So we want to concentrate on the gate to semiconductor interface here. What happens when high energy particles from some source, it might be that your electronics are flying in space, it might be that cosmic rays are hitting your computer chips, it might be that you're operating in a nuclear reactor. In any of these cases, some high energy particles might be flying through your device. High energy ionizing radiation can create broken bonds either at the interface, so we can get some interface states, or fixed charge inside of the oxide itself. And as we've discussed before, either of these quantities of charge can modify the threshold voltage of the MOSFET. So in extreme cases, it might mean that your MOSFET goes from working perfectly to not turning on when it's supposed to when the appropriate gate voltage is sent by the rest of the chip. In those cases, the chip might be permanently damaged. Now, this interface charge can also be made or produced by high energy electrons injected into the channel, so-called hot electrons. So first, let's define what hot means. I'll go back to our density of states for a moment. So here's our energy, density of states. And if we look at the actual population of electrons in the conduction band, for a thermal population, it looks something like this. This square root density of states times the Boltzmann tail, the exponentially decaying Boltzmann tail of carriers. So this is what a thermalized electron distribution looks like inside the conduction band as a function of energy. This is the number of carriers versus their energy. Now, hot electrons might have some other distribution. For example, a non-thermalized hot electron population that has a lot of kinetic energy over a narrow energy range might look like this. How would that happen? So if we have this structure, especially with a short channel length, we remember that our V source drain is applied over a very small distance, giving it a large electric field. And that means these electrons, once they're injected here, can be accelerated to very high energies as they fall down this potential gradient. So they might be moving at the saturation velocity by the time they enter the drain. And that means if they're going past this oxide interface, there's a chance that they'll actually run into atoms actually at that interface. And when they do this, they have enough kinetic energy to actually move that atom off of its perfect lattice site, or its perfect bonding site, and actually create interface charge. So this form of this form of damage could be considered a form of internal ionizing radiation in a sense. The fact that the transistor itself is working at such high electric fields means that the very carriers that are making the device work can destroy it over time. So accumulation of these broken bonds would again change the threshold and other characteristics of the MOSFET itself, causing drift in performance versus time and eventual failure. So in this little section, we've considered ways in which the MOSFET can be damaged over time, as well as ways of sort of temporary modes of operation, undesirable modes of operation, which would move its performance away from the designed parameters. So all of these effects are come about, are consequences of this lateral and vertical and horizontal scaling that accompanies the shrinking of transistors to keep up with Moore's law. And current designs need to take all of these mechanisms into consideration in order to make devices that will last for many years.